Hello everyone, I hope you are doing well. In this video, you will see the perturbation treatment of Stark effect corresponding to the first excited state of hydrogen atom. Now, this video is a requested video. The similar video is already uploaded, but the language of instruction in it is Urdu Hindi. So if you prefer Urdu Hindi as language of instruction, then the video link will be in description box. This video is in English. It is a requested video for those who don't understand Urdu Hindi. So all those videos that you want me to translate in English, you can request me in comment section. I will definitely do it. So let's see what's the problem is. Now it's related to Stark effect, you can see here. Okay, using the first what we have to do is using first order perturbation theory. Now why it's degenerate, we'll see why it is. Using first order perturbation theory, we need to calculate the energy levels of the n equals 2 states of hydrogen atom placed in an external uniform weak electric field along the positive z-axis. It's not necessary that the word Stark effect is mentioned in it. You can also see its definition. The definition could be there as the Stark effect is actually the effect that is produced to the energy levels of hydrogen atom when the hydrogen atom is placed in an external uniform weak electric fields. Okay, this is actually the Stark effect. So the effect is produced, the effect is reflected in the energy levels of the hydrogen atom. The energy level splits, so we need to calculate those energy levels after the splitting process is done. So before doing the problems, it is always recommended that you thoroughly study the theory related to the problem, as the theory related to this problem is degenerate perturbation theory, and the video is already uploaded, and if you want to see it, I will put its link in description box. Otherwise, if you have done on its own, then it's fine also. So do study the theory before doing the problem. It will make your understanding even better about the problem. And now let's see the problem thoroughly. Now here we need to calculate the energy levels. Okay, energies corresponding to n equals 2 state of hydrogen atom. Now n equals 2 state is first excited state of hydrogen atom. Okay, the first excited state of hydrogen atom occurs for n equals to 2, while the ground state occurs for hydrogen atom occurs for n equals 1. Okay, the least quantum number is 1 for hydrogen atom corresponding to its states. So the ground state occurs for n equals to 1, while the first excited state occurs for n is equals to 2. You need to understand that sometimes it's mentioned that calculate the energy level for the first excited state. So you should know what's the n value corresponding to the first excited state for hydrogen atom. As for different systems, the quantum number is different. For example, for harmonic oscillator, the ground state occurs for n equals to 0, while the first excited state occurs for n equals to 1, and so on. Okay, so for different systems, the n values or the quantum numbers value could be different. So it's not a general rule that always the first excited state will occur for n equals to 2. Okay, it depends upon the system and what their allowed quantum numbers are. So for hydrogen atom, n equals to 2 state means the first excited state. Okay, now the first excited state of hydrogen atom is degenerate. Okay, while the ground state is not. In exam you do not have to mention these things. Okay, these are just for making you understand. You will start from this point. You don't have to remember it properly, but to make sure that you understand the pattern. So first excited state is degenerate for hydrogen atom with degeneracy given by the degeneracy for hydrogen atom. Let denote that degeneracy with D. You can in some books the degeneracy is mentioned or denoted by F, it's upon U. I am denoting it by D. So the degeneracy for hydrogen atom equals n square for a particular n state. Okay, now if you put n equals 2 for first excited state, we get the degeneracy for the first excited state of hydrogen atom, which will be 2 square, which is 4. Okay, so the first excited state of hydrogen atom is 4-fold degenerate. Okay, the degeneracy fold degenerate, you will say it like that. So the first excited state of hydrogen atom four-fold degenerate. Whatever number you get for the degeneracy, you say that that particular state is dash fold degenerate. Okay, so we have found the degeneracy, which is 4. Now degenerate states means the states which have similar energy. Okay, for hydrogen atom the energy depends upon only n value. Okay, here it is n equals to 2. For each n value we have 0 to n minus 1 L values. Okay, so n here is 2, so if you put right there, so what you get is 2 minus 1 is 1. So 0 to 1, which is 0 and 1, are L values. Okay, for each n value these are the L values. I hope you know the quantum numbers, and for each L value they are minus L to L m values. So for this L value 1 there is minus 1, 0 and 1 m values. Okay, and for 0 it's 0. Okay, so you can see here that n is equals to 2 state corresponds to different further quantum numbers that have similar energies, and they results different states correspondingly. These are the m values, these are the L values. So the combination of n, L, m, the possible combination that we get for these three quantum numbers is 4 for the n is equals to 2 state. Okay, so that is why we saw here the degeneracy is 4. Here keep that in mind that we have ignored the spin quantum number. Okay, the spin quantum number is not mentioned here. That is why the degeneracy is n squared here. When the spin quantum number is also included, the degeneracy formula gets changed. Okay, so if you consider spinless particles and for hydrogen atom, then for n is equals to 2 state there are the 4 possible quantum states. This is 2 1 1. Okay, one combination of NLM that corresponds to one quantum state, then 2 1 0, that's another state, 2 1 minus 1, that's another state, 2 0 0, that's another state, and together they make 4 different quantum states that have similar energy. Okay, because n is same for these different states, that is why the energy will be same also, and this is what we call as degeneracy. Okay, that the different states having similar energy. So the possible wave vectors that we have here, let's call the first one as phi 1. Okay, that numbering is arbitrary, you can take any of them. So in general, let's put m right there and we'll write a ket vector like that. Okay, with n, L and then m quantum number and as a ket. Okay, so this is the general this m and this m is different. Okay, they are not same. Both of them are different. In book we have took m as a notation, that is why I took right there. So for first, let's say first wave vector, possible wave vector occurs for 2 1 1. Okay, this is the first ket, first wave function, first state. Second, let's say, is 2 1 0. All right, and third is 2 1 minus 1, 2 1 minus 1. All three combinations will be mentioned. Now last one is 2 0 0. From this tree diagram we just got the 4 possible state for the hydrogen atom, for the corresponding to first excited state of hydrogen atom. In all of them, if the unperturbed hydrogen atom is considered, the energy of all these states is same. Okay, if the electron is in this state, this state, or this state, or this state, the energy will be same in all the cases. But if that system, that hydrogen atom is placed in some external uniform weak field, then the energy for the 4 states is not necessarily to be same. Okay, the energies become different, and we'll see what will be the energy corresponding to all these 4 states when the system is placed in an external field. That is what we are going to know, that what is their final energies. Okay, let's say if the unperturbed system is considered, you will mention all these things. Okay, this thing will be you will mention this thing also, because these states is important to be mentioned while doing the problem, because you will use that notation. Okay, at first place it was arbitrary to choose what will be the phi 1, what will be the phi 2, what you will call as phi 3, but after you have set them, you will take this representation in this allocation of numbers onwards throughout the problem. You will not change it. Okay, firstly, at first step it was arbitrary, but once you have fixed it, it's like fixed throughout the problem. Okay, since we are writing it in a ket form, so write it like that also. Okay, put the ket notation over these phi's also. If I call phi 1, then it means I'm referencing to this wave vector, and if I call phi 2, then I'm referencing to this wave vector and so on. So after deciding these, let's say the energy for the unperturbed hydrogen atom, let the energy for unperturbed hydrogen atom for first excited state, or in other words for n is equals to 2 state, is E1, that corresponds to that it's for first excited state, and a 0 on the superscript, that shows it's a 0th order energy correction. That means it's a energy for unperturbed hydrogen atom. This is the energy for unperturbed hydrogen atom. We'll find out the energy for the new system, perturbed hydrogen atom. At the end, we have to go through some of the process. We have to find out the energy corrections corresponding to each state, and then after that we'll be able to find out the energy levels for the n is equals to 2 state. Until now, we have successfully seen the situation where we have seen what is the degeneracy of the hydrogen atom for the first excited state, and it was 4 for the spinless particle case, and we have found the possible wave vectors. Okay, after getting the degeneracy, then we found the possible states, or the possible wave vectors that the hydrogen atom has for the first excited state, and after designating them proper name, we have supposed a particular notation for the 0th order energy correction for the unperturbed hydrogen atom. Now perturbation. Now we need to calculate the perturbation for given configuration is, now the perturbation I'm denoting it with H prime is equals to negative of dipole moment of electrons dot the E field that has been applied. Okay, so the energy, the additional that is applied on the electrons is negative of dipole moment dot E. This is the additional electric energy that the electrons experience. So that is the perturbation, and D is the dipole moment, and we know that the dipole moment of electron is minus E, which is the charge on electron, times the position vector R. Okay, this is not a vector product, this is just a multiplication sign. Position vector R dot E is the electric field here, as it was given that the electric field was uniform, so there is a constant magnitude, times it was directed in positive z axis, so we can write a unit vector k vector that represents the positive z direction. So the uniform electric field can be expressed as the product of that constant field's magnitude, which is E, let's say, times the k vector, unit vector, which is a unit vector along the z direction, that shows it's directed along z direction, so I'm writing it like that. Okay, so since minus minus is plus and E is a constant quantity, so it comes out, and this E is also a constant quantity as the uniform field shows. So R dot k vector is something that is left. Now R vector is a position vector, that means x I hat plus y j hat plus z k hat, and its dot product with k hat is there. Now if you find out the dot product, so only similar unit vectors will get multiplied, the other ones effect will nullify here. So z k hat dot k hat is something that is left, and z k hat dot k hat dot k hat is a scalar product, and it is equals to 1. So we are left with E, capital E times z, and this z is here acting as an operator when it comes in quantum mechanics. Okay, so this hat doesn't represent the unit vector's nature, it is representing that it is a operator. So this is perturbed Hamiltonian operator, which is equals to E charge on electron times capital E, which is the magnitude of the electric field, and times z operator. Okay, so this is the perturbation for our case. All right, now we need to draw the matrix, and the matrix, let us represent the matrix with HP. Okay, this will be a HP matrix, and this matrix will be a 4 by 4 matrix because the degeneracy was 4 by 4. Okay, it depends upon the degeneracy. If the degeneracy is 5, then the 5 by 5 matrix will be formed, and if the degeneracy is 4, then 4 by 4, and so on. Okay, now let us write the member of the matrix, because the matrix will be a lengthy one. That is why I'm taking the larger space. Now the member of the matrix will be decided on the basis of this summation, which is running from I equals 1 to D, where D means the degeneracy. Here the degeneracy is 4, so the summation will run from I is equals to 1 to 4. Okay, equals 4, and here is the get bra notation, which will I'll make it clear what it represents. It's I here. Okay, so H prime is perturbation here. Okay, this is a scalar product where H prime is a perturbation that we found as E, capital E, times Z operator. Okay, and psi I of 0. Here the first member of the matrix will occur for I equals 1. Okay, the second member will be for I equals 2, the third member will be for I equals 3, and the fourth member will be for I is equals to 4. For each row, the m value will be held constant. Okay, and the m value will run from m equals 0 to 4 also. Okay, and these wave vectors are actually the wave vectors that we have designated at the first place. As you can see, we have designated psi 1 as a proper wave vector. Okay, psi 2, psi 3, and psi 4. So it will be made more clear to you when we will write them. For a given row, we'll take m equals 1 as constant. Okay, and it will remain constant throughout the row, and while the I will change depending upon which position in row it has. For example, for first position I will be 1, for second position I will be 2, and for third position I will be 3, and so on. Okay, so taking m is equals to 1 as constant. Okay, in place of m it will be 1 here. Okay, 0, that shows it's 0th order, then H prime as it is, and let me write it for all the row, because it will be same throughout the row, as I told you. Alright, 1 will remain same throughout the row, and what will change is I, and it will be 1 for the first place, and it will be 2 for the second place, as you can see here, and third for the third place, and it will be 5, 4 of 0 for the fourth place. Alright, and next on, m is equals to 1 is done, so next in order is 2. So we'll take it as constant, and we'll write it throughout the row. Okay, alright, and we'll write psi 1 of 0 here, then psi 2 of 0 here, psi 3 of 0 here, and psi 4 of 0 here. Okay, we'll repeat the similar procedure to write the whole members of the matrix, and 2 is done, so it's time to fix 3 here. Okay, the first member is always remained fixed throughout the row, so it's like that. Alright, and it will be psi 1 of 0 for the first place, psi 2 of 0 for the second place. I hope you are getting what I'm doing here. Okay, this summation shows the position, shows the members of each row. Okay, for a given m, and the last member is for 4. So I hope you now understand how I'm writing it. After that, we'll put their values, and we'll solve that summation. We'll solve that matrix, simplify it, and after that few more steps, and we'll get the energy levels. The degenerate perturbation is not an easy thing, you know. Okay, we have successfully written the HP matrix. Okay, and this is it. Next on, we know that psi 1 of 0, we have let it as 2 1 1, psi 2 of 0 as 2 1 0, and psi 3 of 0 as 2 1 minus 1, and psi 4 of 0 as 2 0 0. Okay, in the first place this is something that we have supposed. Okay, and we'll move with it throughout. I haven't mentioned zeroth order on them, so mention them. That will be a good thing to do. So these are the wave vectors that corresponds to these ones. Okay, now we need to put these values over there. Okay, since I'm writing it as a ket, so these are the ket vectors, wave vectors, and we'll put these vectors in place of these ones. Okay, it will be a lengthy one, that is why I'm for phi 1 of 0 we'll put 2 1 1 throughout the row. Okay, in place of psi 1 of 0, 2 1 1 in place of psi 2 of 0, 2 1 0, psi 3 of 0, 2 1 minus 1 in place of psi 4 of 0, we'll put 2 0 0. Okay, so I'll be right back after writing in place of them their values. And for h prime you will write e into this e times z hat. Okay, and since e and capital E are constant, they will come out of the scalar product, and we'll take it common as here. Okay, and only z hat will be left right there. So I'm doing it directly. I hope you will get it. This is what we get. So this is what we'll get after putting the values, and these are the whole bunch of scalar products. And e into capital E, I took it common from the whole matrix, and only z hat will be left in the center region. Now since z hat in spherical coordinates is equals to r cos of theta. Now the next step is to simplify this matrix, and to simplify it we'll use some of the facts, mathematical facts that we know about integrals. And for the first fact is, for those kets which are ket and bras which are very equal to each other, like 2 1 1 and 2 1 1, these are all these diagonal kets are equal to each other. Okay, ket and bras are equal to each other. For example, if you consider this bra and this is ket, both of them are same. Okay, this bra and this ket, 210 210, both of them same, both of them are same. And similarly these two are also, and z is being multiplied with them, where z is a odd multiple. Their product will be an even product because they are both of them are same, and their square will be there, and the square of anything is always an even function, and z is odd function. So if we'll calculate this scalar product, it will come out to be 0, because z being multiplied with this even function makes it odd overall, and their volume integral is 0 mathematically. So these diagonal entries will become 0. Okay, so in simplification, first thing that we have done is that the diagonal entries are 0, and this is 0, and this is 0, and all these diagonal entries will be 0. Now next on, if we consider right there, z in spherical coordinates depend upon r cos r and theta, like z is equals to r cos theta in spherical coordinates. Okay, and we know that the spherical solutions of hydrogen atom results in 3 quantum number. Due to radial component we have n quantum number, due to theta component we have l quantum number, and due to phi dependence we have magnetic quantum number. So since z is being multiplied with these wave functions of hydrogen atom, okay, and the z is only depending upon r and theta, so it will disturb the wave functions of radial and theta component, hence n and l will no longer help us, but the phi one will help us, because the phi component will remain unchanged, and the scalar product will be such that it will be only non-zero if m is equals to m in bra vector is equals to m in ket vector. Okay, if m in bra vector is equals to m in ket vector, only in that case the scalar product will be non-zero, otherwise it will be 0 because of the orthogonality condition. Okay, if you are interested in getting this point in more detailed way, then let me show you. If you are interested, you can skip it if you don't want to get the main reason, the explained reason. So we have this wave function, scalar product, and if we write it in a integral form, then phi 210 with static over there, that shows the complex conjugate. Then z comes, and then the last wave vector, which is psi 2 1 1, and their volume integral. Okay, now z is r cos theta, so if we break psi 2 1 of 0 in its radial component, this is radial component. Psi 1, that shows the L quantum number for theta component, okay, in static over there. And psi 0 of phi component, okay. Similarly, r cos of theta in place of z, and phi 2 1 1, similarly we'll write it for it. Psi 1 of phi, and dv means r square dr sine theta d theta and d phi. Okay, and by law, by rule, all of these integrals will separately be solved. This is, let's say, the radials integral with all these radial values being solved. Okay, and the other one will be for theta, and the last one will be for phi, and that's something that we are interested in, psi 1 of phi and d phi. Okay, all of them are being multiplied to each other, whatever they are, that doesn't matter. If you consider this one, okay, there is no additional phi individual being multiplied, but they are here. And by the theory of hydrogen atoms wave functions, we know that they are normalized wave functions, okay, orthogonal wave functions. So for orthogonal wave functions, the scalar product, this scalar product is only, this integral is only non-zero if the quantum numbers are equal to each other. If the quantum numbers are not equal to each other, then the integral will be 0. Okay, from orthogonality condition, this is something that is fixed, and this condition needs to be fulfilled, because there is no change in the phi wave function due to this new member, this foreign member being multiplied. So this orthogonality condition that we know from theory for hydrogen atom will apply on the phi component, and it will help us to solve this matrix. And all those scalar products for which m is not equals to m in ket is not equals to m in bra will be 0. Okay, for example, here you can see the m vector, the m is 0, and here it is 1, so they are not equal to each other, and hence they are 0. They'll be 0, this will be 0 2, because it is -1 here and 1 here. It's 0 here and it's 1 here, it will be 0 2. Okay, all these members are 0. If I write it side by side, 0 0 and 0. All right, and the next one is 1, and here it's 0, so this one becomes 0 2. Okay, it's 1 and -1 here, it will become 0 2. It's 0, and that doesn't matter because it's 0 from the other property of integrals. So -1 and 0, this will be 0. 0 and 0, this is, they are equal to each other here, so it will not be 0. This one member in second column will not be 0, and we need to calculate it at the end. 2 1 0 0, and here 0 also. Okay, this is 2 0 0 and 2 1 0, because the m values are same, so it will not be 0. And 1 -1, it is 0 2. 0 -1, it will be 0 2, and it will be 0 2. So this one is 0 also, and the last one is 1 0. This will be 0. This will be 0, but this one will not be 0 because the m values are same. So 0, and this is 0, but this one is not, and it is like that. Okay, we have simplified it a lot much, and there is only a few more steps that are left. Now we can see here, we need to calculate this scalar product, as we already know the wave functions for hydrogen atom. So I'm directly writing it, their result. We know that, you have to mention that, we know that this scalar product is equals to -3a naught, and we can see here that both of them are complex conjugate of each other. This is 2 0 0 here in bra, well it is 2 0 0 in ket, 2 1 0 in bra here, and 2 1 0 in ket here. So they are both complex conjugate of each other. If we take complex conjugate on both sides, we'll get the value for the other one. Since all of them are real quantities, so what we'll get is again -3a naught. Since there is no iota right there, so it will not change its polarity or any other thing. So the value is same for this one and this one, that is -3a naught. Okay, and hp prime equals, if we put its value right there, what we'll get is okay, in next step we'll take -3a naught as common from the whole matrix, and we'll get E minus 3a naught, and it's this matrix that is left. Okay, so AHP prime equals minus 3a naught E into capital E, and this is the H matrix that we have found. Now we will diagonalize this matrix in order to get the eigenvalues, and those eigenvalues will be actually the energy corrections for the hydrogen atoms first excited state. Now let us diagonalize the HP matrix as we have found it successfully. For diagonalizing it, we will first find out this thing, okay, where I is the identity matrix whose order is same as that of HP matrix, that is, it will be 4 by 4 identity matrix. And after finding out this thing, we'll take out its determinant and we'll put it equal to 0, and we'll find out the possible lambda values that we will get as a result, and those lambda values will be actually the energy corrections, first order energy corrections for the first excited state of hydrogen atom. Okay, so first of all, I'm writing here the HP matrix, which is minus lambda times I matrix, which is identity matrix, and identity matrix have non-zero members only in the diagonal, okay, and those are all 1. If you multiply lambda with all of these members, you will get lambda in place of them, okay, and you need to do the same in this side also. You need to multiply this with this matrix so that we can subtract both of these matrices properly, and only where the members are non-zero you will get this. Okay, now we need to subtract both of these matrices, and for subtracting 0 minus lambda means minus lambda here. 0 minus 0 is 0, 0 minus 0 is 0, 0 minus 0 is 0. Okay, corresponding entries will be subtracted with each other. So 0 minus 0 is 0, 0 minus lambda is minus lambda, 0 minus 0 is 0, minus 3a naught E, E minus 0 is minus 3a naught E again. 0 minus 0, 0 minus 0, 0 minus lambda is minus lambda, 0 minus 0 is 0, 0 minus 3a naught E again, 0 minus 0, oh, it's lambda over there. 0 minus 0, 0, 0 minus is minus lambda. Okay, this is the matrix that we get. Okay, now we need to put its determinant equal to 0, and it's like that. This is a determinant sign. This is the process that we follow in order to find out the eigenvalues for the matrices, and this is something that we study in linear algebra. This is the process for finding out the eigenvalues, that is also known as diagonalization process, and I put it equal to 0. Now what we have to do is find out its determinant, and that is simply the first entry, that is minus lambda, and this row and column being ignored. These are the entries that we'll write. Since all these entries are 0, other entries in row are 0, that is why this is it. Okay, now we'll find out its determinant again, and it's minus lambda, this one minus lambda here, and this minus lambda again here, a big bracket, and this row and column being ignored, and it's minus lambda 0, 0 minus lambda. Then second entry is 0, that is why we'll ignore it, and third entry, that is minus 3a naught E into E, okay, into this row and column being ignored, and this is 0 minus lambda. The other entries that are left are these ones, equals to 0. Okay, these are 2 by 2 determinants, and we'll calculate its value, and it's minus lambda into minus lambda with diagonal entries being multiplied. Minus lambda into minus lambda is lambda square, minus sign from formula, and 0 is the product of the other diagonal entries. So that is it. And for the other ones, these two give 0, minus from formula, and the other two's minus is plus, and lambda into 3a naught E into E, okay, equals 0. Now let's simplify it. Minus lambda into this will become lambda cube, okay, with negative sign, okay, and minus 3a naught E into E as it is. This being multiplied with these entries, which are minus 3a naught E into E lambda, okay, equals 0. minus lambda cube, it's minus minus plus. 3 into 3 is a 9, a naught square, e square, capital E square into lambda, okay, and equal to 0. If you take one lambda as common, then we get lambda square minus lambda square as common, plus 9, a naught square, e square, capital E square equal to 0. So we'll put all these values equal to 0 because some of them are. So one is this lambda. For this lambda we will get lambda equals 0. This lambda maybe also equals to 0. We'll call it as lambda 1. This one lambda 1 and this is lambda 2. Okay, for the different possible solution that occurs for there, because if you multiply these two lambdas over there, it will become a fourth power equation which will have 4 possible solutions. So 2 of them are lambda equals 0 and the other one is lambda equals 0, and the third, and for the other ones we'll put this one multiple equals to 0, and if we solve it we'll get, if we take lambda square on the other side, this is something that we'll get, taking under root on both sides will give us lambda equals plus minus 3a naught e into e, and if we write the other the different solution with the proper name, let's say it's lambda 3, which is the positive solution, lambda 4 is negative solution. So these are the different eigenvalues that we got. Okay, and these are the energy corrections actually, and okay, we got energy correction lambda 1 equals 0, another energy correction as 0, third energy correction as 3a naught e into capital E, and fourth energy correction is minus 3a naught e into capital E. Now these are the energy corrections, but what are the wave functions, what are the states, eigenstates whose eigenvalues correction is these ones. Now the correct zeroth order wave functions needs to be determined whose eigenvalues corrections are these ones. Okay, so let us now determine correct zeroth order wave function corresponding to these corrections. Okay, for that purpose we'll use the eigenvalue equation. These are the energy corrections, first order energy correction, and their proper wave vectors needs to be determined, and that is what we are going to do. So their wave vectors can be determined using the eigenvalue equation, and if HP matrix being applied on some wave function, let's say x, that will give us this eigenvalue lambda 1 and x again. Okay, this is the eigenvalue equation. We'll do it separately for all eigenvalues and we'll get the value corresponding to x, and we'll find out the correct zeroth order wave function, and this is the eigenvalue equation that we are going to use. And before doing that, let zeroth order wave function be, now the zeroth order wave function, let's say उसको मैं psi से represent कर देती हूँ, ठीक है, psi m or 0, that will be equals to c1 phi 1 of 0 plus c2 phi 2 of 0 plus c3 phi 3 of 0 plus c4 phi 4 of 0, while these wave vectors are actually the ones that we have supposed at the first place, which were these ones. From this eigenvalue equation we will get the value of c1, c2, c3 and c4. Okay, and in 1 x equals c1, c2, c3, c4. Okay, this is the method to write a zeroth order wave function where each c1 is a multiple of this ket, c2 is a multiple of this ket, c3 is a multiple of this ket, and c4 is a multiple of this ket. Okay, so x is something like that, and let us do it now. Now HP matrix was minus 3a naught e into capital E. Okay, rewrite it. Okay, into x, which is c1, c2, c3, c4, that equals lambda 1. Lambda 1 was 0 into c1, c2, c3, c4. Okay, I am just putting the value of x, HP and lambda 1 right there. Lambda 1 was 0, so this is something that we'll get. And after multiplying 0 with all these members, we will get 0 here, here and here. Okay, now we need to multiply these matrices together, and let us multiply this one with this matrix first. That will result as minus 3a naught e into e here and minus 3a naught e into e here. Okay, now we'll multiply both of these matrices together, this member with the first member, second row member with the second member of the column, third with the third one, and the fourth with the fourth one. Okay, so if you multiply all these, we'll get 0 as a result. Okay, as the first member, because all of them are 0, they being multiplied with all of them and being added will result 0, and this 0 with C1 gives 0, plus 0 into C2 is 0, 0 into C3 is 0, minus 3a naught e into C4 is not 0, actually it's minus 3a naught e into capital E C4. All right, and for third it's 0 again, and for the fourth is a minus 3a naught into capital E C2. Okay, this one member, the last one member. I hope you know how to multiply the matrices. Okay, so now the next step is to equate the members of the matrices, the first member with the first, second with the second, third with the third, and fourth with the fourth, and only the non-zero ones will be considered, as you can see here. And minus 3a naught e into e C2 equals 0. Okay, these being divided on the other side will give us C4 equals to 0, and this will give us C2 equals to 0. So for lambda 1 equals to 0 eigenvalue, correct zeroth order wave function is psi 1 of 0 is equals to, actually I designated this psi 1 of 0 equals, we'll put C2 and C4 equals to 0. C2 and C4 will be 0, while the other ones will be not 0 because their value is not specified, so they will be taken as general ones. Okay, this is the correct zeroth order wave function for the eigenvalue correction lambda 1 equals to 0. Okay, and its energy level is, its total energy will be the zeroth order energy correction plus the new energy correction that we got, which is 0 here, so plus 0, which is again E1 of 0. Okay, so this energy level remain unaffected even when the external weak electric field is applied. So this is the first zeroth order wave function with this energy level. Okay, now for lambda 2 equals to 0, the similar wave function will result. So for lambda 1 equals lambda 2 is equals to 0, the correct zeroth order wave function is also similar. So both of them states are eventually, we can call it as the one state. Okay, because both of them have similar energy level and their correct zeroth order wave function is also similar, so it means it's the same state. If wave function is same, then it means the state is same. So both of these energy eigenvalues will correspond to a similar state. That state is the linear combination of these two quantum states. Okay, so their superimposed state have this energy level with 0 as the energy correction. Now let us calculate the correct zeroth order wave function for lambda 3 equals 3a naught e into capital E, and lambda 4 equals this one. Okay, so now we are going to calculate the correct zeroth order wave function corresponding to these energy corrections, and for lambda 3 equals 3a naught e into capital E, the eigenvalue equation is this. Okay, now putting the values, and this is something that we get. Where lambda 3 is 3a naught e into capital E, and C1, C2, C3, C4 as it is. All right. So now we will multiply these two matrices together, and before doing that I am just taking 3a naught e into capital E as common, because we can see here it could be cancelled out on both sides as it is right there also. So in addition to taking it common, I am also multiplying this matrix with this matrix, and we will now imagine minus 1 right there instead of 3a naught e into capital E, as we have to common this one factor outside. So multiplying this one with this, then this with this, third with this, and fourth with this. Okay, and we'll add the results up and we'll do it for all rows one by one. Okay, so for the first row, we'll multiply 0 with C1, then 0 with C2, we'll get 0, 0 with C3, 0 with C4, and we'll get 0 again. And we'll do it for other rows also, so that is what we will get. And for the last one, we get, as this is non-zero, into C4. Okay, and again 0 plus 0 plus 0 plus 0 for the third row too, and for the last row we'll get this. Okay, while the other side contains this one thing. Now we'll cancel both of them, and 0 minus 3a naught e into, oh my god, it's minus 1. Okay, because we have took this common, so this is actually minus C4 only, 0, and minus C2 only. 3a naught e into capital E was taken common in the previous step, and I do it always, so be careful. Now we'll equate both sides, and we'll put this one equals to this, first member equals to first member, second member C2 equals this, C3 equals this, and C4 equals minus C2. Okay, so we can see here that C1 and C3's values are 0, while C2 equals minus C4, or equivalently C4 equals minus C2 is something that we get. So the third wave function, correct zeroth order wave function, will become, it was something like that. Okay, now we'll put the value C1 equals 0, it will become 0, and this one also 0. And since C2 equals minus C4, so simply we'll put minus C4 in place of C2. Okay, or put C4 equals minus C2 if you don't want to put its value. Okay, you will put only one value at a time, and this is something that we'll get. We'll take C4 as common, and we will get minus 210 plus 200, and C4 into, I'm writing 200 in first place and this one in second place, and using the orthogonality condition we can find out the value of C4, since this wave function, this correct zeroth order wave function, should be normalized. So their coefficient square, okay, should add up C4 square minus C4 square plus C4 square should be equals to 1. So the coefficients of these cats, their squares and their sum should be equals to 1. Okay, so minus C4 with square is again C4 square plus C4 square equals 1. Okay, when we are writing the wave functions in terms of cat, the normalization condition is written as the coefficient and their square, and for all of the cats, and their sum should be equals to 1. So this was the coefficient for this one cat, and this was the coefficient for this one cat, their squares, and we are adding them up, which will become 2C4 square equals 1, and C4 square equals 1 by 2, and C4 taking under root on both sides will become 1 over under root 2. So 1 over under root 2 is the value of C4. We'll put it right there, and this is the wave function, correct zeroth order wave function, corresponding to the energy correction of 3a naught, positive 3a naught into E. Okay, and for this correct zeroth order wave function, the energy level that we will get is the energy level corresponding to this is, let's say it is E3, will be zeroth order energy, okay, that we have supposed at first place for the unperturbed system, plus the energy correction that we got, and we'll put its value right there, and this is the energy. Okay, this is the energy level corresponding to this state. This is again a superimposed state. You have to consider the theory in order to understand what is zeroth order wave functions. So yeah, okay, one of the wave function was for the energy correction lambda equals to 0, and energy level was E1 with order 0. Okay, and the third and second one is 3a naught E into E with energy level as this. Okay, and you can see its wave function. Now we'll calculate it for minus 3a naught E into E. So when it's minus, so this minus will cancel out simply, and what we will get is this condition. You can solve it on your own now because the method is quite clear. This condition will become like that, the positive ones, and you will get positive right there. Okay, and this is the wave function with plus sign as the fourth zeroth order wave function, as the one of the state, and it's like that with plus sign, and it has corresponding energy correction as minus 3a naught E, and energy level corresponding to that state is E1 of 0 plus lambda 4, which was E1 of 0 minus 3a naught E into E. Okay, so all in all we got three splitted states. Okay, one of them was E1 of 0 with energy level E1 of 0, the other one is with energy E1 of 0 plus 3a naught E into E, and another one is this one. Okay, so the unperturbed hydrogen atom that has degenerate states, that all in which all the four states having the similar energy E1 of 0, it's split it into three states when the weak electric field is applied on it, and their energy levels are right there, and their correct wave functions that we got are these ones. Okay, it has the one that we got at first place, that was actually you know now that what it was, and for this energy correction, for this energy level, this was the energy this was the wave function state, and for the last one, this is the wave function state. So in the presence of electric field, there are the three states, and all these three states have different energies, so the splitting is threefold. So in this problem, what we had done so far was, first of all, we found the perturbation for the case that we have. This perturbation is actually the extra energy that we are giving to the system, which was in that case this one. Okay, and after doing that, we found the degeneracy of the state that we are considering. Okay, that is under study. That for example, in that case, it was the first excited state of hydrogen atom, so we found its degeneracy, and then after finding the degeneracy, we found the possible wave vectors or the wave functions are the states that the system has. We found the four states that we named as phi 1, phi 2, phi 3, and phi 4. And after doing that, what we did is we formulated HP matrix, and that HP matrix was formulated by using a simple rule that was this one. Okay, so this is the general rule that we will follow, and where these psi's are actually these wave vectors, possible wave vectors, they correspond to this. And after designing the matrix, we need to simplify it. We need to find out the scalar products that are written as the member of the matrix, and after finding out the scalar products, we'll simplify it, and we'll get a simplified HP matrix. And after getting the HP matrix in simplified form, we'll diagonalize it, and for this we'll subtract it with this matrix lambda into I, where I has the similar order as the HP matrix has, while the HP matrix order depends upon the degeneracy. If the degeneracy is fourfold, it will be 4 by 4 matrix. If it is sixfold, then it will be a 6 by 6 matrix, and so on. Okay, so after doing this subtraction, we'll take its determinant and we'll put it equal to 0. We'll find out the possible lambda values that we'll get as a result, and each lambda value that we'll get, we name it as different result. Okay, that we just like we did right in this question. And after getting these lambda values, these are actually the energy corrections, okay, eigenvalues, and we'll add these energy correction with the unperturbed hydrogen atoms energy. Correspondingly, we'll get the energy levels, all the energy levels. And to get the wave function, the states actually that has these energies, we need to follow the procedure, and we'll use the eigenvalue equation, and we'll get the eigenvectors for these eigenvalues. All right, so the question is done, and I hope you understood it well. And if you have any queries, you can ask me in comment section, and I tried my best to make it clear to you people, and I hope you will share it with others, and like, share and subscribe. Thank you.